Today, we will delve into the fascinating interplay between the Poisson distribution and fatigue failure, particularly in the context of ski lift usage. We'll explore the fundamentals of the Poisson distribution, its practical applications, and how it relates to cyclic stress and fatigue failure in engineering.
The Poisson distribution is a statistical tool used to model the occurrence of discrete independent events within a fixed interval of time or space. It's handy in queuing theory, telecommunications, and reliability engineering. How does it work? At its core, probability describes the likelihood of an event occurring. The Poisson distribution quantifies this likelihood for events that happen independently. Independence means that the occurrence of one event does not affect the probability of another event occurring. This is crucial for the Poisson model as it assumes that each event happens independently of the others. The Poisson distribution defines the distribution of binary data from an infinite sample, meaning it can model the number of times an event occurs in a large number of trials or over a large period of time. The Poisson distribution is particularly useful for modeling events that occur over a certain period of time. It provides time-dependent distribution of the probability of a given number of events occurring in a fixed interval. For example, it can model the number of customer arrivals at a store in an hour or the number of emails received in a day.
The probability mass function of the Poisson distribution is given by the formula below, in which mu is the average number of times an event occurs, x is the actual number of times that a specific event occurs, and E is the Euler's constant. This formula calculates the probability of exactly x events occurring in a fixed interval when the average rate is mu. Traditionally, lambda is used in place of mu, but in this course, mu is predominantly used to symbolize the average number of events. Okay, now let's look at some example data. To illustrate, let's consider a ski resort where mu is 120 car rides per hour, and we want to determine the probability that exactly 115 cars will be ridden on a particular Sunday. So as we're given mu, which is 120 car rides per hour, and x, which is 115 rides, we can plug these values into our PMF formula to find a probability. This calculation involves evaluating the exponential term, raising mu to the power of x, and dividing by the factorial of x. The result gives us the probability of observing 115 rides in an hour when the average rate is 120 rides per hour. After having plugged all of these values in and solving, you should get an end result of 0.03345, or approximately 3.3%. Bear in mind that once you add all of these probabilities together for, let's say, for example, 116 rides and 117 rides and so forth, you should get a total of 100%.
Now let's shift gears to discuss fatigue failure, a critical consideration in engineering, especially in the context of ski lift mechanisms. Fatigue is the initiation and propagation of cracks in a material due to cyclic loading. Over time, repeated stress causes these cracks to grow, eventually leading to failure. Once cracks form and propagate, failure can occur rapidly, even if the material is initially sound. Cyclic stress refers to the distribution of forces that repetitively change over time. This is common in mechanical systems where components experience regular unloading and loading cycles. In a ski lift, cyclic stress occurs as the lift repeatedly carries passengers up and down the slope. This repeated loading and unloading can induce fatigue in critical components.
Ski lift application part 1. So, how does the Poisson distribution model the frequency of ski lift usage, and how does this relate to assessing and managing cyclic stress? Modeling frequency. Usage frequency. The Poisson distribution can be used to model the number of times the ski lift is used within a given time frame, such as rides per hour. This helps in understanding the operational load in the system. Probability estimates. We can predict peak times and ensure the lift operates within safe limits by estimating the probability of different usage levels. Assessing cyclic stress. Repeated stress monitoring. Poisson probability estimates allow us to monitor the frequency of usage and the corresponding cyclic stress. High usage periods correlate with increased cyclic loading on the lift components. Crack propagation. The bolts and other connecting mechanisms of the ski lift are subject to fatigue failure. By understanding the usage patterns, we can predict when these components might fail and schedule maintenance accordingly. Preventing catastrophic failure. Data integration. Integrating Poisson probability estimates with known data on fatigue failure stresses and lifetimes enables us to predict potential failure events. Preventative maintenance. Regular inspections and maintenance can be scheduled based on these predictions to prevent catastrophic failures, ensuring the safety and reliability of the ski lift.
The same problem can be approached from a different perspective. The next example shows how a ski lift manufacturer or service company might use a Poisson distribution to determine how many emergency repair crews they will need to keep on standby during the ski season. Breakdown frequency. The Poisson distribution can be used to model the number of times a ski lift will need maintenance within a given time frame, such as breakdowns per week. Applied across all the ski lifts one company might be responsible for servicing, this would help determine how many repair crews should be on standby. Peak repair demand. We can predict the likelihood that X many ski lifts will break down during a given week. Staffing more repair crews increases costs, but resorts having to wait to get their lifts repaired means lost revenue and customer dissatisfaction. Optimize risk. A compromise needs to be made, so an acceptable probability of repair delays will need to be determined. If that threshold is 1 in 100, then you need to find the minimum number of ski lifts breaking in a given week that has a probability less than 0.01. That number of ski lifts is the number of repair crews needed.
In conclusion, the Poisson distribution is a valuable tool for modeling frequency and probability as exemplified by our example of ski lift usage. Understanding the cyclic stress and fatigue failure mechanisms would help in assessing the reliability and safety of ski lifts. By leveraging statistical models and engineering principles, we can ensure that machines operate safely and efficiently.